So back on this previous Wednesday, we talked a little bit about classification of robots. What's some of the ways we classified them by? Huh? Their type of intelligence? Okay, what else? Huh? Yes. So there's a lot of different ways you can classify this, guys. It's one of the biggest ones we got to classify by, so we can even make it work. Type of power it uses. Is it all electric, or is it hydraulics or pneumatics? That's probably the biggest one, right? So it's going to determine the place you can put these. Specific. So there's a lot of different ways to classify it. What's one of the other ones? What about workspace? And the work envelope and what that looks like. Y'all remember that? You have Cartesian, you have, come on, Cartesian, cylindrical, spherical or polar, and then anthropomorphic or there's another name for it, but I can't come up with it. So we're going to talk a few more things about classification. Now, why do we want to classify robots? Why do we need to know what kind of classification they are? Type of job they're going to be used for? What was yours? It lets you know what kind of environment you can put it in. Do I need to put it on the Mars or the moon? Or do I just want to put it in a warehouse where all it does is stack and remove product? It's going to determine a lot of things, right? Do y'all know what an actuator is? Does anybody want to guess what an actuator is? Hmm? Kinda, but not quite. Okay, so the actual definition for a actuator is it takes drive power, like electrical, hydraulic, or pneumatic, and converts it into motion. Does that make sense? That is the definition of an actuator. It takes your drive power and converts it into motion. So you have linear actuators and you have rotational actuators or rotary actuators. Um, a lot of, let me back up. Motors are considered a rotary actuator, for example. If you've ever seen a hydraulic or pneumatic setup, anytime you have a moving part, those are actuators. Like I said, the very definition of this, excuse me. So the very definition of an actuator is something that's going to take a signal, a power signal, and turn it into motion. I want to write that down because this is not the first class you'll hear it from. It certainly will not be the last. No, actuators are what would actually make the wheels turn. Okay. Huh? We use them a lot in hydraulics and pneumatics. That's why my brain is stuck on that. But essentially, any machine that creates movement is a type of actuator. Actuators come in three types. You have partial rotation, full rotation, just like a clock or a motor, and then you've got the linear actuator that just has the ability to move in and out. Okay. If you're using hydraulics pneumatics as the main base for that particular set, it's taking pneumatics and literally converting air into movement through just one actuator. Could be a motor, could be a piston. Those are actuators. So the actuator stroke is the total extent of actuator movement. Now, that depends on type of actuator you're dealing with. If you're dealing with a motor, I'll have to see if I can't dig one up. If you're dealing with a motor, it does not have a maximum rotation. Does that make sense? However, you have a lot of rotary actuators that are only partial rotations. Kind of like a seesaw, they'll just move back and forth in a rotating manner. You have the linear actuators that the furthest out that they can get is the size of the cylinder you've got it in. So the actuator stroke is the total extent of the movement. Hard stops. They're pretty much what they sound like. So a hard stop, the whole purpose of a hard stop is to keep your machine from going further than it should. Does that make sense? So what we're talking about here is, hold on, let me grab something. Hard stop. This is actually the robot y'all will be using, except y'all will not have this little plate on it. But if you look, there's a little plastic tab right here. That tab makes it to where this robot cannot go past its base here. Now, why would you need something like that? Well, on robots that, and I'll pass this guy around, guys, just try to be easy to control. Hard stops are for robots that don't remember the term, nothing else but the term servo motor. Okay? So the whole purpose of a hard stop is to make sure that the robot can't do something like a 360. These guys have hard stops as well as program stops. What that means is that you can only go so far before the robot sits there and goes, no, I'm not supposed to be here. Nope, you can't move me into this space. And the whole purpose of that is to protect the internal workings of these. All right, so let me kind of give you a food for thought here. If you take any kind of electronic and you keep spinning, spinning, spinning on one side of it, what's going to happen to all the wires inside? What's going to happen to all the mechanicals inside? It's going to tear them up, right? So hard stops are meant to stop that. And like I said, these guys actually have program stops, which the program stops do exactly the same thing, only they're in a program form instead of a physical form. Physical form is for very low-grade robots. Okay, they're the ones that can do a repetitive task and they don't have to change that task. All they got to do is put a cap on toothpaste all day long. All right? So that's the reason we use hard stops. Okay. So stepper motors. This is a DC motor that rotates in single steps in response to an electrical pulse. I don't think I've got one in here. I'll have to dig one up here in just a little bit. I know Rich has several. But a stepper motor, that says, stepper motor quite literally moves in steps. But it does not have the ability to count the steps. Does that make sense? In other words, it doesn't know what step it's on. Okay? Every time you turn the stator of this motor, it has no clue what you're actually doing. It's just saying, oh, I might have moved. They don't have any feedback to sit there and go, yes, you moved. Yes, you did something. Now you need to not do that. And here's two of the biggest terms right here, open loop and closed loop. So an open loop system relies on actuator movement and limiting devices of the arm for positioning. Put it to you a different way. That's very long-winded. Open loop robots have no feedback. They don't know what's going on around them. We use physical parts of the world to help them with their job. But they don't know what's going on. Does that make sense? All they're doing is they're doing their job day in, day out. Come down, screw a cap on toothpaste. Come down, screw a cap on toothpaste. That's all it does 24/7. That goes back to, this is the robot that if you have minor issues in your line or you're changing something up, it's a pain in the rear to do it. But it's a cheaper option than one of these guys. Does that make sense? Versus a closed loop system, which is what these guys are. Okay? And they get feedback from the motors themselves in their arm. They know exactly what position everything is in at any one time. You can literally go up to these guys. There's a certain part of the teach pendant that will pull up and show you where he currently is at every single joint. They're closed loop robots. They know where they're at. They know what they're doing. Open loop, not so much. Does that make sense to everybody? Kinda, sorta. So basic classifications. Control system, is it open loop or closed loop? In other words, does it have feedback somewhere in its makeup? Does that make sense? The arm geometry, what kind of a workspace and what kind of geometry do you need to work with this? Okay. Your drive source, which is electrical, hydraulic, pneumatic, and what is the purpose you're using it for? Okay? What is the purpose you're using it for? Is it going to be just basic assembly, non-assembly, doing whatever, or mobile? Okay? The other thing we have is path control techniques. You have continuous versus point to point. We'll talk a little more about that here in just a second. And intelligence level. Now, I've said it before and I'll say it again. Intelligence level, the way that they write that is very misleading. Okay? Because robots technically have no intelligence. We can make them seem intelligent with very clever programming. But do they have any real idea that they are a robot and this is their world? They don't get to have the existential crisis a human does, right? So with intelligence, you have high intelligence, low intelligence. Again, I would be very, very careful when you're trying to tell somebody a robot is intelligent. Can it think for itself? No. It needs you to think for it. So this particular little guy is a Cincinnati, I can't ever say that, Micron. It's a T3-363. This guy is a high technology, closed loop, electrically powered cylindrical robot with a point-to-point path and is primarily used for material handling. And all that sounds great. High technology, that means I can probably go in and program it and it will actually understand the program. Closed loop means that I've got something on there that's giving it feedback. Some way to tell where it's at, what it's doing. Electrically powered, that's fairly typical. Why? Because electricity is very abundant, right? We have electricity in most countries that use robotics and manufacturing. And they're becoming more and more prevalent as we go, right? It's a cylindrical robot, which means that what should I expect is that this guy can spin left to right and move up and down, maybe in and out. But he has a very limited space within a cylinder. Okay. Point to point, we have not really covered that. We're going to. And what is it primarily used for? This one's material handling. So classification by control system, we have two types. We have open loop, which again, no feedback. Y'all know what feedback is, right? Okay. No feedback is given to an open loop robot, which means it has no idea what's going on. Okay? Basically, it's on autopilot. Then you have closed loop. This one does have feedback. It can look at position and speed. Yes? Open loop is very low intelligence or low technology. If we weren't having class over there, I'd show you all on the line. But there's what's called a gantry robot. And what this gantry robot does is it moves along this one slide. It can move left to right, and it moves up and down where it can grasp and move different things it's manufacturing. We don't classify it as high intelligence because it just runs the motor until it hits the stop. Then sits there and goes, oh, I'm here at the stop. Drop down, pick up whatever you've got to drop and get down, and then it pulls itself back up and moves it over. But it has no idea if you like stop it right in the middle of its track and don't let it move, it doesn't know that it's done that. It sits there and goes, oh, so I guess I must drop here. I'm at the end of my rope. Does that make sense? That's open loop. Closed loop are these guys that are accurate with speed as well as position. They are very specific to within micrometers of where they are. Okay. So a closed loop provides feedback, an open loop does not. That is the most basic way I can say that. All right, so we have two different types of paths that a robot can follow. You have a point-to-point, or you have continuous. This particular one is where they're showing you a point-to-point robot program. We'll get into that some more here in a little bit. Okay. So open loop. Robot is placed in the correct position by an actuator stroke with fixed hard stops or variable hard stops. It uses stepper motors and timers. In other words, it does not have a lot of intelligence. It's mainly running off of timers, and it's looking for it'll run till it hits something and then it'll stop. I don't know, I'll turn this off. There we go. All right, so that's open loop. Open loop is exactly what this little yellow robot is. He's completely open loop. He has no idea and you'll find out when we get to lab. He has no idea where he's at. He doesn't know what he's doing. He's just hanging out, waiting for you to put him in the right position that you need him in. So actuator stroke. This is the total extent of actuator movement. You have linear and rotary. Okay. So total extent of actuator movement, it can be linear or rotary. So linear strokes with hard stops. Anybody know what this actually is? It's a cylinder or an actuator. So what it's supposed to do is, what does an actuator do again, guys? Yes. So it's waiting. This particular one is either hydraulics or pneumatics. I can't really tell. But it's, yeah, right there. Compressed air. So it's looking for air to push into the cylinder so it can push against this base and extend your rod. Does that make sense? So it's taking air power and converting it into linear motion. Quite literally. Okay? And then it uses compressed air or a spring to push it back to its normal position. In this case, they're using compressed air. Fully extended means that the base is going to sit snug up until till it can't move anymore. And then the stroke is exactly how far does it extend past itself. So what we put instead, if we don't need that full extension, are hard stops. Okay? Hard stops are exactly what they sound like. They make sure that this cannot either extend or retract completely. It stays in the zone that you need it to be staying in so that it does its job more efficiently. Does that make sense? Huh? Yes, that's what they're calling the collar right there, the white line. So, how to say this? So what you do with a lot of these cylinders, if you're going to put hard stops, is you have to put something, you can't grab the cylinder itself, okay? And if they take a break, I'll bring one over for y'all to look at. All it is a smooth piece of aluminum, and you don't want to grab that because if you damage that rod in any shape, form, or fashion, it's toast. You can't use it again because there's no way to repair it. And these things can cost quite a bit. So the way that they've come up with, instead of trying to grab the cylinder itself, the rod itself, excuse me. So instead of trying to grab the rod itself, use something like, they call it a mechanical dog. There's several other ways you can call it, like a tag or a whatever you want to call it. But all it is something that fits across the rod and allows you to keep the position of the rod where you want it to be, especially whenever you're using hard stops to help move it. Does that make sense? So this guy has variable hard stops. Now, first of all, what kind of robot do you think this is? What do you think it moves in? What's its arm geometry? Give y'all a little hint here. It's able to move up and down, it's able to move left to right, and I think this moves in and out. So what is the arm geometry of this robot? Rectangular. It has it moves in a rectangle. Does everybody see that? So robots with variable hard stops. So this guy has the ability to stop itself before it hits the end of its frame, I guess you could say. These are variable stops. So why would we want to use variable over non-variable stops? Hmm? You want to be able to move them because you might have to adjust something, right? What would be a downside to having those be variable? Hmm. That or somebody comes along and starts messing with them. How many of y'all know the people that go, ooh, what does this button do? Next thing you know, everything's all screwed up and you're just going, why did you touch the button? You're not supposed to touch the button. Okay. So stepper motors, and again, I'm going to see if I can't find one here in just a little bit. So they're actually quite interesting little motors. It rotates in very precise steps and is rated in the number of steps per revolution or number of degrees per step. They use a permanent magnet rotor and control circuit. The control circuit applies voltage to make the motor step. Excuse me. So essentially every time you apply voltage, this thing goes over another step. Okay? All right, this should give you a good example. So this is a good example of a stepper motor. It moves in steps. Does that make sense? All right. This is an open loop robot system. So why would we choose open loop versus closed loop? What do y'all think? Mm-hmm. Very good. So the advantage of open loop is low cost with high repeatability and controller simplicity. Okay. If you just need something that's cheap, quick and easy, and it's a repetitive job that's not going to change, open loop's way to go, right? However, you don't really have control of the speed the robot moves at. There's a lot of work if you have to change the position, because you're going to have to finesse it 6 ways to Sunday, right? And precision work in work cell fixture placement, in other words, you cannot shift anything in this robot's work area, or it will be thrown off for a very long time until you can finally get it dialed back in. Okay. That makes sense to everybody? So this is great for material handling and machine tending, because it's just a mindless task, right? And anything you can give something else a mindless task for, better than a human having that same mindless task, because what happens to humans over time? We get bored, we get complacent, and we quit paying attention to what we're doing, which leads to risky situations or accidents. Okay. So basic servo systems, again, servo motors give feedback. They know where they are at all times. Okay. So the drive signal to the servo, you get a feedback signal from the sensors. It has its own position and speed sensors internally. And everything talks back to that controller again. All right. So closed loop, jointed, spherical robots. Basically, going back to all this, you have everything's got to talk back to the controller, including the motors. And then the motors are told what to do by the controller. The desired tool center point can be put anywhere within the robot's work envelope. It is not limited by the position of mechanical stops. The controller continuously knows the robot's position and can change drive power only when necessary to correct position. Okay. But the advantages of it is that you can reprogram it easily. You can. That's the great thing about these robots, is that you can reprogram them anytime, anywhere, anyway. You can change the program points, unlike a open loop robot. You can have complex manufacturing tasks with this particular robot and multiple program storage and execution. However, you are putting down a large capital investment. What does that mean? You're shelling out a lot of money, right? That requires a higher skill in maintenance. So the applications are far bigger with this. Why? Because we can do a lot more with it. Welding, painting or coating things. Do you know why gaskets are so precise now? It's because generally they have a robot doing it, and they can run that robot to put that bead of silicone right where they want it, so nothing gets messed up. It's harder for a human to do because we're going to miss stuff, we're going to gap things and everything else. Arc and water jet cutting inspection. Yes, a robot can inspect things. What you do is you put a camera on it, and you set the camera vision systems up to look for certain things here and there, and then once it either finds it or doesn't, it'll send the signal to the computer. Inspection complete, this is what I found. And assembly. Okay. So assembly, you have exit repeatability, rigid and strong, non-assembly, or general purpose. Okay. So non-assembly, of course, things like painting or welding. General purpose, I've seen robots that have like a whole tool belt right in front of them so that they can do assembly. Or it could just be general purpose, depending on what you got. And then you got the mobile robots, which if you've ever seen anything about Amazon, they got a lot of those. Quite interesting little robots. They look like glorified Roombas. Okay. So these right here are ones that can run independently. Like I said, this right here is like an oversized glorified Roomba. Because all it does is move around on the floor. You can add other stuff on top of it to help it do other jobs, but it's a glorified Roomba on its own. All right, any questions on classification of robots, guys? All right, so here's the deal. I've got to get some of the labs copied. I did not realize I don't have enough copies of it up until I started looking at it. So that being said, I'm going to go ahead and give y'all about a 20-minute break. Sound good? I'll try and get some of these papers in order. But guys, if y'all need anything, I'll be right back. I'm going to run down the